On Earth, it is summer 1981. Over 1 billion kilometers away, a spacecraft approaches the ringed planet, Saturn. This complex robot is part of humankind's continuing effort to better understand the solar system. Not long ago, our planetary neighbors were only hazy disks, dimly seen through our telescopes. But through the electronic eyes of spacecraft, they have become known worlds, seen close up for the first time. Come, let us explore these worlds, so different from our own.
About 2,000 years ago, a Roman philosopher said, "Nature does not reveal her secrets once and for all." That certainly has been true in our attempts to understand the Earth and also the other planets. People have been studying the heavens for thousands of years, first with their naked eyes, then with telescopes, and then more sophisticated instruments. But it's only been in the last 20 years that we've begun to understand how the planets got to be the way they are. Planets are shaped by a number of fundamental factors. One of these is gravity. The size and gravitational pull of a planet determine what kinds of elements it can hold on to. Distance from the sun is another factor. That determines how much energy a planet receives from the sun. And then there are internal processes that operate on planets. We see the result of one of these processes right here. I'm standing on a lava flow. Volcanoes show that the Earth is hot inside. This internal heat causes far-reaching changes on our planet. For one thing, volcanoes pour out vast quantities of molten rock and so reshape the surface. The internal heat also causes the interior of the Earth to circulate and parts of the crust, called plates, to drift in different directions. The movements of the crust are very slow, only a few centimeters a year. But over a long period of time, they build great mountain chains where the crustal plates collide. And they produce ocean basins where the plates drift apart. Another important geologic process is erosion. Erosion, primarily by running water, gradually wears down the continents and changes the landscape. The upshot of it is that the Earth's surface today looks far different than it did, say, 100 million years ago. About 3/4 of the Earth's surface is covered by water, and the entire planet is covered by a thin atmosphere. Now, this is where gravity and the Earth's distance from the sun come in. We have an atmosphere partly because the Earth's gravitational pull is strong enough to hold on to fairly light substances like water vapor, nitrogen, and oxygen gas. We have liquid water on the surface because the Earth is the right distance from the sun. The atmosphere traps a sufficient amount of heat to prevent the ocean from freezing, but not so much as to cause it to boil away. Without an atmosphere, the Earth would be a far different place. It might look like the moon. It's very close to us in space, but it has no atmosphere, no water, no life. Our exploration of the moon showed us that it is nearly a dead planet today. But it provided one very important piece of information. It showed us the great importance of meteorite impacts as a fundamental process that shapes the surfaces of planets. We know now that the moon, as well as all the other bodies in the solar system, were heavily bombarded in their first billion years. Then about 3.5 billion years ago, this bombardment slowed to a bare trickle as most of the solid chunks of matter were swept up by the planets. The number of impact craters tells us almost at a glance whether the surface is young or old. Lots of craters mean the surface is very old. Few craters tells us the surface is relatively fresh. Here, for example, a new surface was formed by outpouring of lava. But the lava flows are still more than 3 billion years old. Little has happened on the moon since then. But on Earth, internal activity continues. That's one reason why we don't find many impact craters on Earth, like this one in Arizona. They get erased by one or another of Earth's geologic processes. So the picture of the Earth that we have today is that it is a dynamic and restless planet with a relatively young surface. A lot of things have gone on in the past, and a lot will continue to happen in the future. Although it's 4.5 billion years old, the Earth is still evolving.
The inner planets are Mercury, Venus, the Earth, and Mars. They really form two pairs. They're all small and rocky, but Mercury and Mars are about the same size. Venus and Earth are about the same size. Although they have similarities, there are spectacular differences among these four bodies. Let's take a closer look at the inner planets, starting with Mercury.
Mercury, the smallest of the inner planets, is a barren world.
Nearly covered with meteorite impact craters. There has been almost no geologic activity on Mercury for more than 3 billion years. Because of its low gravitational pull and the intense heat so near the sun, Mercury has no water and very little atmosphere. In fact, it probably never had very much.
Venus is the second planet from the sun.
Venus is covered by a thick atmosphere of carbon dioxide, 100 times as dense as the Earth's. And virtually the entire planet is wrapped in clouds made of small drops of sulfuric acid. Studies done with radar showed that Venus closely resembles the Earth in that it has mountains, craters, plateaus, and great continents. Venus may have had oceans early in its history, but they disappeared long ago. It's not known whether there still is volcanic activity on Venus today. The surface temperature of Venus is hot enough to melt lead. This tremendous surface temperature is caused not by the planet's internal heat, but by the so-called greenhouse effect. The atmosphere of Venus allows light from the sun to reach the surface, but much of the light is then changed to heat, which is trapped by the thick layers of carbon dioxide.
A similar thing could happen on the Earth if the carbon dioxide in the atmosphere increased enough. The question is, how do we prevent that from happening on the Earth? Well, let's go on and look at Mars.
Mars is about half the size of the Earth and about 80 million kilometers farther from the sun. Surface temperatures on Mars can get low enough to freeze carbon dioxide. The many impact craters in some areas show that parts of Mars are very old. But obviously, many changes took place on the Martian surface long after the early meteorite bombardment stopped. There are great volcanoes on Mars, all extinct now, including the largest volcano known in the solar system. There is a huge canyon system that cuts across 4,000 kilometers of the surface. There is a sand desert that is the largest one known anywhere. And much to the surprise of scientists, they found channels and islands eroded by great floods of water. But the question scientists wanted to answer more than any other is there life on Mars now? Some tests showed the Martian soil to be very active, as though there were life there. But other tests showed that there was no organic material in the soil at all. So is there life on Mars? The best answer seems to be probably not. But there may have been life in the past, and future exploration of Mars might turn up fossils preserved in the rock layers.
Mars is in an ice age now, but at several times in the past it's been much warmer because enormous quantities of water flowed on the surface. The question is exactly when did that happen and why? And is it connected to similar changes that have taken place on the Earth? If we can find out when and why this took place, we may be able to anticipate future changes like this on the Earth.
Once we get beyond the orbit of Mars, the distances between planets become enormous. Jupiter, the next planet out, is over 800 million kilometers from the Sun. That's about 5 times further away than the Earth. The 5 outer planets, Jupiter, Saturn, Uranus, Neptune, and Pluto, are far different than anything we find in the inner solar system. Except for Pluto, which is an oddball, these planets are larger and far less dense than the rocky planets of the inner solar system. Basically, they're huge volumes of gases and liquids. Jupiter is practically the same composition as the Sun, about 90% hydrogen and 10% helium. Jupiter is a giant of the planets. With more than double the mass of all the other planets put together, it exerts so powerful a gravitational pull that it can hold on to the hydrogen and other gases. In fact, when we look at Jupiter, what we're really seeing is the top layer of clouds in an enormously deep atmosphere. One of the most fascinating features is the Great Red Spot, which was first observed over 300 years ago. This cloud feature turns out to be a huge storm, big enough to swallow 3 Earths. One of the most surprising discoveries we made at Jupiter was that there was a faint ring surrounding it. Jupiter has at least 15 satellites, which form a miniature solar system as they orbit Jupiter. The 4 largest satellites of Jupiter form a particularly fascinating story. We think they're composed mainly of ice and some rock. And you would think in the extreme cold so far away from the Sun, where ice freezes to a solid as hard as rock, that these objects would be geologically dead. And that does seem true for Callisto, the outermost of Jupiter's large satellites. This is an icy world almost totally covered by impact craters, an extremely ancient surface. But as we get closer to Jupiter, the satellites become more and more dynamic. Here's Ganymede. Lots of impact craters in some areas, but we also see features that show that parts of the surface are relatively young. Europa has hardly any impact craters at all. And this is the satellite Io. Not a single impact crater to be found anywhere. Far from being a geologically dead world, it is one of the most active bodies in the solar system. So far, we've discovered at least 9 active volcanoes on Io, the only place other than Earth that we've ever seen volcanic activity. It came as a total surprise to everyone that these satellites should be so different from one another, and they should show evidence of continuing internal activity. And the surprises continued at Saturn. Saturn is almost a twin of Jupiter in size and composition. Saturn too is kind of a mini solar system with its 23 or more satellites. Saturn is about 1.5 billion kilometers from the Sun, and therefore extremely cold. But even out here, we see signs of internal activity on some of the satellites. There are, of course, the usual impact craters, but in addition to these ancient surfaces, we also see some very, very young ones. Evidently, some internal processes are still going on here today. But you mention Saturn to people, and right away they think of rings. They're made mostly of small ice particles that have been pulled by Saturn's gravity into a thin layer less than 1 kilometer thick, but over 250,000 kilometers wide. The rings may have formed when a satellite broke up into pieces, or they may be chunks of ice that were never able to come together to form a larger body. We see a lot of activity in the rings, In fact, we can see the patterns in them change almost from minute to minute. Once we leave Saturn behind, we know less and less about what's beyond. Distances are so vast that we have trouble getting any good information. These photographs are about the best views we can get of Uranus and Neptune, although we've used other sophisticated techniques to get a pretty good idea of what they must be like. If all goes well, in a few years, a spacecraft will be flying past these planets and sending back even more detailed information. Uranus is tipped almost 90 degrees toward the sun. It has 5 known satellites, and in 1977, a system of 9 rings was discovered. Neptune has at least 2 satellites, but no rings that we know of. When we finally get data from our spacecraft, we'll probably find that Neptune and Uranus also turn out to be active, dynamic systems like Jupiter and Saturn. And this is Pluto, right now just a point of light in our largest telescopes. In fact, the only reason we can tell it's a planet is because from night to night it moves against the fixed background of the stars. Pluto has a satellite, which we can see as a small blob on an enlarged image of Pluto. It's thought that Pluto and its satellite are made of frozen gases. Some scientists don't even think Pluto is a true planet, but merely an escaped satellite of Neptune. And are there any other planets beyond Pluto? Well, right now we don't really think so. But like so many other questions in planetary science, it's one we can't answer for sure just yet.
Many of the details are still unknown, but the outline of how the sun and the planets came into being is clear. Before there was a solar system, there was a solar nebula, a vast cloud composed mainly of hydrogen and helium. Slowly the nebula condensed and separated into distinct bodies. The largest of these became the sun. Several planets, each made up of a slightly different mix of materials from the solar nebula, took shape at various distances from the sun. Early in its history, a strong wind of particles from the sun blew most of the lighter elements far into space. The heavier elements left behind formed the rocky inner planets. These are relatively small because the solar nebula contained little of the material that rocks are made of. The gaseous giants formed in the deep cold far from the sun. These planets are huge because hydrogen and helium were plentiful to begin with. A few large bodies in the solar system are nearly dead worlds today, but they are the exception. Almost everywhere we have looked so far, the planets and their satellites have proved to be surprisingly active. Conditions on some planets have changed dramatically and relatively quickly, not just once, but several times. This includes Earth. At present, conditions here are very favorable for life. But this may change, either through natural processes or through our own doing. If we learn in time why conditions changed on other planets, it may teach us how not to cause unintended and possibly harmful changes on our own planet.